Good morning, students. Today we will discuss about the electric potential and electric equipotential surfaces, electric potential due to a point charge, electric potential due to a conducting sheet, and electric potential due to dipole. All these content in this video. It comes under the unit 1, electric field intensity and potential. Okay. So the content under this chapter is electric potential and equipotential surfaces, potential due to a point charge, potential due to dipole, and potential due to a circular disk. So first of all, we have the definition of electric potential. What is electric potential? The electric potential is at a point. We always define the electric potential at a point in the electric field. Okay, if there is nothing, if there is no electric field, there is no electric potential. Therefore, the electric potential at a point in the field is the ratio of work done in bringing a charge, a test charge, from infinity to that point against the force of repulsion to the magnitude of the charge, magnitude of the test charge. Okay, therefore electric potential is the ratio of work done to the magnitude of the charge. So this is work done to the magnitude of the charge. What kind of work is doing here? The work is done against the some force of repulsion force, okay, which occurs between the main charge and the test charge. Okay, therefore suppose we have a positive charge here. It has some electric field around the charge. Okay, if we kept a test positive charge here, okay, it has a force of repulsion and it moves in this direction, okay, due to the force of repulsion. If we bring this charge from here to some at a point in the field, okay, against the force of repulsion, so in that case we are doing some work. Okay, we are doing some work. So that work divided by the magnitude of the test charge. Magnitude of the test charge gives us the electric potential at that point. Okay, the electric potential varies from point to point. So we have one electric potential here and one electric potential here. Okay, everywhere the electric potential varies with the distance, isn't it? Now the units for electric potential is joules per coulomb. Why? Because we have the units of joule for the work and coulombs for the charge. So hence we have joule per coulomb, or it is equivalent to volt. So joule per coulomb or volt. So we will measure the electric potential with the joule per coulomb or volt. Next, equipotential surfaces. Equipotential surfaces are the locus. The definition of the equipotential surface are the locus of all the points which have the same electric potential is called electric equipotential surfaces. Okay, so let's have a look of this is the expression for electric potential due to a point charge. This is the electric potential due to a point charge. So here the potential is inversely proportional to the distance r, inversely proportional to the distance r. Okay, the distance increases, potential decreases. Okay, so it is proportional to the 1 by r. Okay, so the electric potential is inversely proportional to the its distance. Hence, so the let equipotential surface, let have a look at the, let's have a look at the equipotential surfaces. Suppose we have a positive charge here. Okay, so this is the distance of the first circle, radius of the first circle. So at this point, suppose we have a value of V1, electric potential V1 here. So on every point on this circle, it has the same value of V1. Why? Because it is only dependent on the distance. Okay, therefore the every point on the circumference of this circle, the electric potential is same. Similarly, suppose if we take the third circle, on the circumference of this third circle, at every point the electric potential is same. So the locus of all these points are called equipotential surfaces. So inner circle is a equipotential surface, the second circle is also a equipotential surface. Okay, so the circumference, every point on the circumference of the circle is a equipotential surface. Similarly, suppose if we have electric potential in this direction, so we have suppose let it be a distance r from the charge. So at a distance r we have some value of electric potential. So on the every point on this line we have the same potential. Similarly, we have another value of electric potential on the which is having the same value on this every point on the line. So these lines are also called equipotential surfaces. Okay, so the equipotential surfaces are the surfaces which are having the same value of electric potential. Okay, now the potential due to a point charge. Potential due to a point charge. Suppose we have a positive charge here. Okay, we have a point B here and a point A here. Let's have a test charge Q0. Okay, let's have a positive test charge Q0 here. Okay, suppose the work done in moving a test charge Q0 through a small distance dr. Okay, suppose let E be the electric field due to this point charge. Hence the force on this test charge is Q0 E. Okay, the force on the test charge is Q0 E. So with that force we have to bring this charge in this direction, in this direction opposite to the against the force of repulsion. Okay, so the work done in bringing this test charge through a distance dr is given by, what is the formula for work done? Force into displacement. What is the force here? Q0 E. Q0 E into what is the distance? dr distance. So Q0 E into dr. Q0 E dot dr. F dot dr. Okay, this is equal to Q0 E dr cos 180. Why? Because